Look at this photograph of a storefront window. The vintage televisions inside appear completely clear, with their proportions and positioning mathematically intact despite the thick glass barrier between the lens and the subject. Yet, when you shoot video or take photos through thick glass, you will frequently capture offset ghost reflections or secondary light spots that don't belong to the original objects. This diagram illustrates the core of refraction. When a light ray traveling through the air hits the denser glass, it slows down and bends sharply inward toward the perpendicular normal line. But tracing that single bent line is an incomplete picture. To map exactly how flat glass manipulates an image, we have to track the multiple reflections happening at the exact same time as this entry bend. Look closely at the top interface in our model. The moment the main beam enters, a small fraction of the light instantly reflects off the external surface, mirroring the exact angle it arrived at. Following the primary ray down to the bottom boundary, the medium changes again. As the light exits into the air, it speeds back up and bends away from the bottom normal line. Right here at the exit, some light is trapped. It reflects internally off the bottom glass-to-air boundary, bouncing right back up into the slab. That faint, trapped internal ray eventually exits on a secondary path. This specific rogue light wave hits a camera sensor slightly offset from the main image, creating the visual artifacts we call ghosting. Returning to our diagram, we have a geometry question. Why doesn't this thick slab rotate our view like a triangular prism? The answer lies in the relationship between the initial angle of incidence at the top and the final angle of emergence at the bottom. Pause the video here. If you apply Snell's law to the change in refractive index at this bottom boundary, how do angles I and E mathematically relate? At the top interface, the entering equation equals n times the sine of r. The exiting equation at the bottom perfectly mirrors it. Substitute them, and the sines of I and E are equal. The angle of incidence exactly matches the angle of emergence. Because the light enters and exits at the exact same angle relative to perfectly parallel normals, the exiting ray is mathematically locked into a trajectory parallel to the original beam. Looking at the full path across our diagram, the light beam has not rotated. Because its final direction hasn't turned by even a fraction of a degree, the total angular deviation is exactly 0. The light is traveling the same direction, but it has physically jumped to the side. This perpendicular distance between the original path and the new emergent path is called the lateral shift. We calculate that sideways shift using this formula. It requires 3 specific inputs: the overall thickness of the glass, the initial angle of incidence, and the refractive index, which determines the internal angle of refraction. The glass slab acts as a sideways translator for light. By shifting an image laterally without bending its final direction, the shapes and proportions of the objects on the other side stay mathematically intact. In this dual animation, you can see how those specific variables change the outcome. A thicker piece of glass forces the light to travel a longer internal diagonal, creating a much larger sideways shift. But if the light hits perfectly straight on at 0 degrees, the lateral shift completely drops to 0. The shift also depends on the color of the light. Watch the white beam split inside the slab. Violet light has a higher refractive index, meaning it bends sharper than red light, causing the violet wavelengths to exit with a slightly wider lateral shift. This photograph shows an optical laboratory setup. By rotating flat glass windows within the path of a laser, scientists use controlled lateral shift to adjust the beam's physical position by micrometer increments without disturbing its target heading. Calibrating those 3 exact variables, the glass thickness, the incoming angle, and the material density, gives engineers precise command over the physical position of light. Here is the complete visualization of the glass slab. We have our parallel entry and exit rays, the internal ghost bounce causing interference, and the mathematical proof of 0 deviation with a measurable lateral shift. Tracing this exact sequence of bends and bounces gives you the mechanical blueprint for how flat glass processes every photon that hits it.